Hello, everyone. Welcome back. Today, we're going to be doing our first day of Unit 2, Organized Counting. I hope the last test went well, and I hope this test can go well for you as well. Okay, so organized counting. Let's first talk about what are combinatorics. So, combinatorics is a branch of mathematics that deals with methods for counting. And if you're interested in combinatorics, there's actually entire courses you can take at the college level and at the university level to learn more about combinatorics. In this course, we'll just be doing the very, very basics of combinatorics, right? Now, when we say methods for counting, we don't just mean counting 1, 2, 3, 4, 5. We don't mean counting as in the counting you probably learned when you were 5 years old, or maybe less than 5 years old even. We mean counting in terms of how many different ways, how many different combinations or permutations are there in a certain case, and I'll get into that a bit more in a moment as to what do I mean by that exactly. So basically, the multiplicative counting principle basically says if a process made up of steps with separate choices, the total number of choices is m times p, etc., where m is the number of choices in the first step, n is the number of choices in the second step, etc. And before I move on to an example, I want to talk about, well, why is that even true? Right? Why can we multiply all these numbers together and get the answer? Well, let's think about it. Let's say we're ordering a pizza and there's two crust choices. We could either choose thin crust or regular crust, for example. Those are our two choices. And then there's three choices for cheese. We could either do let's see, mozzarella cheese, cheddar cheese, or what's another one? No cheese, right? So there's three options here. There's two options here. So we could multiply those together and get six. So there's six possible pizza orders we could have. But why is that? Well, let's think about it. We could have a regular crust with any of the three types of cheese, with either no cheese, mozzarella, or cheddar, right? So that's three, right? Or we could have any of those three cheeses with the other type of crust, with the thin crust. So we can have thin crust and cheddar cheese, thin crust thin crust mozzarella cheese, or thin crust no cheese. So that's six different ways. Now let's say there's another step where maybe there's three other topping options. We can either get pepperoni, bacon, or pepperoni or bacon or olives, for example. And let's say that for argument's sake that we can't choose more than one topping, even though obviously, in real life we probably could choose more than one topping, I would hope. But let's say just for the simplicity of this example that we can only choose one topping. Well, we could have any of those six combinations we talked about before. We could have any of those outcomes with any of the three new ones. We have to multiply by 3 again to do each of those with each of the new ones. So that's going to be 18 choices now, right? And so you kind of get where I'm going with this, as to whenever we add another layer, we could have any of the previous choices with any of the new choices. So it's going to multiply it by that number. And then now we have those choices, and then we add another layer and any of those previous choices with any of those new choices, and so on. So in terms of, if I was to ask you, oh, how many possible ways are there to order food or to order a pizza at Pizza? Well, probably hundreds or thousands, right? Probably thousands of ways, especially if we do account for the fact that we might have multiple toppings, which we'll talk about how we would solve for how many combinations there are in that case in probably a future lesson. But for now, let's just assume that we have choices. We have three different choices to make, or two different choices to make in that case, and we can only choose one of those choices. Then we would multiply them together, and that's the reason why. So let's get into these examples. The first example says how many outcomes are possible is if a nickel is flipped and then a six-sided die is rolled. Okay, so let's think about that. Well, what are the two things that could happen if a nickel is flipped? We either get heads or tails. So for nickel, it's either heads or tails. So that's two possibilities, right? So two. Right? We either get heads or we get tails. There's no third option, right? The nickel probably wouldn't really land on its side. So it's going to land either heads or tails. Now, if a six-sided die is rolled, that means we're either getting 1, 2, 3, 4, 5, or 6. So that's six possibilities there. So heads could go with any of these six possibilities, making up the first six, or tails could go with any of these six possibilities, making up a second six, right? So we have 2 times 6, which is equal to 12. So there's 12 possible outcomes. We could even list the outcomes. This is a small enough example that I can list the 12 outcomes right now. Not that it asked for that, but just to make sure we're understanding this, I'm going to list out the outcomes. We could have got a head on the nickel and a 1. We could have got a head and 2, head and 3, head and 4, head and 5, head and 6. Or we could have got tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, tails and 6. So those are all 12 of the ways that we could do it. So if we were asked what are the outcomes, we would just list all those outcomes. You probably will not be asked that in most cases, because it's kind of just tedious to write all of them out. However, although not as tedious as our last unit, but regardless, you're a lot more likely to be asked how many outcomes are there as opposed to being asked to list all possible outcomes. Okay, very good. Let's move on to number 2. It asks how many outcomes are there if a card is selected from a regular deck of cards and then a day of the week is chosen at random. Okay, so how many cards are there in a regular deck of cards? So there's 52 cards in a deck. So that means there's 52 possible outcomes for the card, right? And keep in mind, we're counting every card as unique, right? So the King of Hearts and the King of Spades are 2 different cards because they have different suits. There's no, there's no 2 cards that are exactly the same. Sometimes cards have the same suit or have the same face value, but no 2 cards have the same face value and the same suit. So there's 52 outcomes for the card. It could either be the 2 of any of the 4 suits. So 2 of hearts, 2 of diamonds, 2 of spades, 2 of clubs, and then 3 of hearts, 3 of spades, 3 of diamonds, 3 of clubs, etc. all the way until we get to the ace of hearts, ace of spades, ace of clubs, ace of diamonds, right? So that's overall 52. I skipped a bunch of numbers. I skipped the 4 of all the suits and 5 and 6 all the way up to, and 7 and 8 and 9 and 10 and jack and queen and king, but you get the idea, right? There's 13 different face values and there's 4 different suits. Good. And then a day of the week is selected at random. Well, there's 7 outcomes for days of the week, right? So this is the outcome possible for days of the week, right? Because either it is Monday or Tuesday or Wednesday or Thursday or Friday or Saturday or Sunday. There's not really any other day that it could possibly be, at least not that I know of. So 52 times 7 is going to give us 364. So there's 364 possible ways that I could draw a card from a deck and also randomly choose a day of the week. Good. Very good. Let's move on to another example. This example says, in planning a trip, a family must choose to either travel to their destination using a car, rental car, or plane. When they get to the city, they must either choose between 8 hotels to stay at. Once they get to the amusement park, they must decide what park package they're going to pay for. The park packages are bronze, silver, gold, and platinum. How many options in total does the family have to choose from for their family trip? Okay, so let's see. What are the different ways they could travel to their destination? They could either use a car, a rental car, or a plane. So that's 3 different options, either a car, although a rental car is a car, but let's just pretend those are different options because I do think that's what they're meaning here, even though technically a rental car would also be a car and a car could potentially be a rental car, but regardless, 3 options. When they get to the city, they must choose between 8 hotels to stay at, so times 8 for the hotels. And I'll write this transport. This is hotels. Once they get to the amusement park, they must choose what park package, and the choices are bronze, silver, gold, platinum. So that's 4 choices, right? Bronze, silver, gold, platinum is 4. So let's say park package. And we're also assuming here that they're not going to choose multiple options. They're not going to choose 2 different park packages or 2 different hotels or 2 different methods of transport. They're just going to choose one thing from each category, because if they had the option of choosing multiple, then we would actually use a different method, which we'll go over a different day. But this is assuming they choose exactly one choice. They make exactly one choice for each of these aspects of their trip, and we get 96. So basically there's 96 possible different ways to do this family trip, basically. Very good. Very, very good. All right. Oops. I skipped ahead. The next one is mutually exclusive events that we'll talk about. So we're kind of going to get into a little bit of a different topic here, and we're going to talk about the adding counting principle next. So mutually exclusive events are events that cannot occur at the same time. So I'm going to give an example of mutually exclusive events. For example, somebody cannot be 5 feet tall and also 6 feet tall at the same time. It can't happen. Someone's either 5 feet tall or 6 feet tall or neither. What's another example? Let's say that the basketball team and the soccer team both meet at the same time each week. Well, I can't be in two places at once. I'm either on the soccer team, or I'm on the basketball team, or I'm on neither of them. So those would be mutually exclusive because they can't both occur at once, right, for the same person, right? So those are some examples of mutually exclusive events because they are events that cannot occur at the same time. It's not possible. Oh, another example back, I guess this goes into a little bit about our what we learned back in grade 12 advanced functions. For those of you who have taken it, it's mutually exclusive events to have for the same function an oblique asymptote and a horizontal asymptote, right? Because when does a horizontal asymptote occur? A horizontal asymptote occurs when the numerator is either the same as the denominator or when the numerator is less. Degree is less than the denominator degree, right? So either the degrees are the same or the denominator degree is less, or sorry, is more, and the numerator degree is less. Whereas an oblique asymptote, well, that occurs when the numerator degree is exactly one higher than the denominator degree, then we have an oblique asymptote. And so therefore, well, what does that mean? Well, that means that they're mutually exclusive because we can't both have it, we can't have a case where the degree of the numerator is exactly one greater than the degree of the denominator, and also simultaneously the degrees are the same or the degrees of the numerator is actually lower than the degree of the denominator. It just doesn't work like that. And so there is no function for which we can have both an oblique asymptote and a horizontal asymptote. It just is not possible. So there's another example for those who have taken advanced functions, which I'm sure probably most of you guys have. So that's good. Okay, so let's talk about the additive principle. It says if one mutually exclusive event can occur in m ways, a second event can occur in n ways, and a third can occur in p ways, then the total number of ways in which these events could occur is m plus n plus p, etc., right? Which makes sense, right? We're just totaling up the number of ways that the events can happen. Okay, so let's do an example here. It says if a letter from the word attendance is selected at random, how many ways can a vowel be selected? Well, let's think about it. Well, there's two A's, and there's two E's. So therefore, there are 4 ways that a vowel could be selected. We could choose either of the A's or either of the E's. So that's four different ways for the vowel to be selected. Let's try another example. There is a bag that contains 12 toonies, 15 loonies, 45 quarters, 54 dimes, and 20 nickels. If you reach into the bag and select one coin, how many ways can that coin be greater than 25 cents? So basically, the toonies are greater than 25 cents, and the loonies are greater than 25 cents. The quarters are exactly 25 cents, so they would not be counted. The dimes and the nickels are less than 25 cents, so they would also not be counted. So we have 12 toonies plus 15 loonies. So that means that in total, there's 27 different ways that a something that's greater than 25 cents, a greater than 25-cent coin, can be selected in this case. Good. Okay, example 3 asks, how many ways can you draw a heart or a black ace from the deck? Okay, so let's do total possibilities. So how many hearts are there? There's 13 hearts, right? There's the 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6 of hearts, 7 of hearts, 8 of hearts, 9 of hearts, 10 of hearts, Jack of hearts, King of hearts, Queen of hearts, I got those in the wrong order, and Ace of hearts. So there's 13 hearts. Now, how many black aces are there? Well, in total, there's 4 aces, right? There's the Ace of hearts, which we already counted in the other one, but that's not a black ace. That would be a red ace. There's also the Ace of diamonds, which is also a red ace. And there's also the Ace of spades and the Ace of clubs. Now, the Ace of spades and clubs are both black aces. So that would be +2, right? So +2 for black aces. Okay, so therefore there are 15 different ways to choose either a heart or a black ace. Now, let's say that these two things were not mutually exclusive. We'd actually have to subtract off the things that we double counted. However, in this case, these are mutually exclusive, right? There's no way to draw something that is both a heart and a black ace because all hearts are red cards and all black aces are black cards. And so, and a card can't be both black and red. A card is either black or it's red. So good. There's our answer. All right, and you know what? That brings us to the end of today's class. Next time, we're going to talk about factorials, which are these explanation points and what they mean in math as opposed to English. So we'll talk about those for the next day. Good work today, everyone, and I will see everybody next day. Bye, everyone.